Hey everyone, welcome back to Trigonometry. This is going to be lecture 11 of the course. And in this section, we're going to continue looking at trigonometric identities of value. And so this time we're going to look at the double angle formulas, the half angle formulas, and the power reducing formula. So we kind of choose to do all three of these together here because they're all related to one another. So let's go ahead and jump into it. We'll call this section 3.3, and that's double angle, half angle, and power reducing formulas. So I'm going to start with the double angle formulas, and I'm just going to start by just writing them out. And then we'll see where they come from. The double angle formulas. So there's three of them. So there's the sine, there's the sine of 2 theta equals 2 sine theta cos theta. Okay, and just we'll pause for a second and look at this one. So this one is, so as the name implies, double angle, right? So if I want to know the value of sine of 2 theta, 2 times that angle theta, then I can calculate that value by calculating the sine of theta, cosine of theta, and multiplying those two together and adding to the product of number 2, right? So 2 sine theta cos theta is the same as sine of 2 theta, right? So that's the first double angle formula. The second double angle formula is for the cosine, and it says cosine of 2 theta is equal to cosine squared theta minus sine squared theta. So these don't look anything alike. They don't look anything alike, but it turns out they actually all are derived in a similar way. And then finally, the tangent of 2 theta is equal to 2 times the tangent of theta divided by 1 minus tan squared theta. Okay, so three formulas, three very different forms. Okay, and so these formulas all are derived from the sum and difference formulas. They all come from the sum and difference formulas. Right, so the sine of 2 theta, that comes from the sum and difference formula for the sine function. And this is actually very easy to demonstrate. I'm going to do the demonstration just for the sine version, just for the first one, and then I'll leave it to you to figure out how the other two are done. But I'll give you a hint, they're done in a very similar way. And so the way this works is, first of all, let's remember what the sum formula is for the sine. So we'll say the sine of alpha plus beta, okay, remember this, is sine alpha cos beta plus cos alpha sine beta, right? So this is the sum formula for the sine. Okay, so using this sum formula, right, what we can do is we can say the following: sine of 2 theta, right? This is just equal to sine of theta plus theta. Okay, right? That's pretty simple. And so pretending your alpha is theta and your beta is also theta, then it's a straightforward exercise. Here you just say, okay, that means this is sine of theta cos of theta plus cos of theta sine of theta, right? And then, I mean, these are the same, aren't they? They're just in a different order. So this is sine of theta cos of theta plus sine of theta cos of theta, right? I can just switch that order. And so this is 2 times sine theta cos theta. Okay, and so that's the formula for the double angle. Okay, and that's how it comes about. The cosine is going to be very much the same. You're just going to think of cos 2 theta as cos of theta plus theta. Okay, and so this is where these three formulas come from. They all come from the sum formulas, sum and difference formulas from the previous section. Okay, let's do an example using this guy, using these. And so here's what we'll say. Let's do this example. If sine of theta equals 5/13 and theta lies in quadrant 2, okay, theta lies in quadrant 2, our task is to find the exact value of sine of 2 theta, cos of 2 theta, and tangent 2 theta. Okay. All right, and so let's, so we're told is that sine of theta is 5/13, and we're told that theta is in the second quadrant. So we should be able to draw a picture here. So let's do that. Let's draw a picture. Here's our grid. This is quadrant 1. Quadrant 2 is over here. So our angle theta must be like this, right? And we're told that sine of this angle is 13, or sorry, it's 5/13, and so that means opposite over hypotenuse, right? So 5/13, like so, and then we'll say this is x, right? So we've got some triangle here. Okay. Now, we can figure out what x is by using the Pythagorean theorem. Okay, so we can use the Pythagorean theorem to find x, and so x squared plus y squared equals r squared. And in this case, we know x squared plus 5 squared equals 13 squared. Right, and so that means x is equal to 13 squared minus 5 squared, and then the square root of that, which we know is, well, and technically it's plus or minus, so let's be careful there. Okay, so 13 squared minus 5 squared is 144. Okay. And then 144 is actually 12, isn't it? The square root of 144 is 12. Okay. All right. And so which one is it? Is it plus 12 or negative 12? Well, it's got to be negative, right? And that's the key here, is that we're in the second quadrant, right? So if the second quadrant, we know the x value is negative in the second quadrant, so this is negative 12. Okay, and so now we've got our triangle. It's a 5, 13, negative 12 triangle, and we'll write it like that. And so we can easily determine what all of these values are, right? So the sine of 2 theta is going to be equal to 2 sine of theta cos of theta, which we know is 2 times 5 over 13. And then the cosine of theta is negative 12 over 13. Okay, and then you can do that multiplication, and you'll see that this is negative 120. So that's 10 times 12 is 120, and then the bottom 13 squared is 169. Okay, and so there's the first one. What about the cosine of 2 theta? Well, we know that that is just cos squared theta minus sine squared theta. We know those two values. They are negative 12 over 13, so we got to square that and subtract 5 over 13 squared. Okay, and what do we get then? Well, we get 144 over 169 minus 25 over 169. And that gives us 119 over 169, doesn't it, for the cosine of 2 theta. Okay, and then finally the tangent, right? This is just a straightforward application of the double angle formula. It's 2 times the tangent of theta over 1 minus tan squared theta. Okay, and the tangent is 5 over 12, isn't it? 5 over negative 12. So this is 2 times negative 5 over 12 divided by 1 minus negative 5 over 12 squared. And so up here I get negative 5/6. Okay, and down below this is going to be, well, all in this will be 119 over 144. Okay, we can do this arithmetic. We'd have to take negative 5 over 6 times 144 over 119. And when we do all of that, you can do some simplifying here, and you end up with negative 120 over 119. Okay. All right, so the problem kind of started out, we had to do a little bit of reasoning about where the triangle lived and what the values of the sides of all the triangle's edges were. But once we did that, then it's a straightforward application of the double angle formula. Okay. Let's talk about the power reducing formula next. The power reducing formulas. Okay. And these again I'll write out. Power reducing formulas. And so the idea here is you have something like sine squared theta. And in this case, sine squared theta is equal to 1 minus cosine, like writing backwards. The sine squared theta is equal to 1 minus cosine of 2 theta over 2. Okay, so this takes the square of the sine function and relates it to an expression that has trig functions in it where the trig function is not squared. But you see you do have a double angle in here. Okay, so obviously these are going to be derived from the double angle formulas. So let's write them all out. The cosine squared theta power reducing formula is 1 plus cos 2 theta over 2. And then for tangent, we get 1 minus cos 2 theta over 1 plus cos. Right? You can probably guess that this one comes from the ratio of these two. Okay, but these formulas all, as you probably have guessed, come from the double angle formulas. And so let's derive the cosine in this case. Let's derive this cosine. So we know that the double angle formula for cosine says that cos 2 theta is equal to cos squared theta minus sine squared theta. Okay, and we know that that's equal to cos squared theta minus, now instead of sine squared theta, I'm going to plug in the Pythagorean identity here, and I'm going to say 1 minus cos squared theta. Okay, we can do a little simplification there, so that's equal to cos squared theta minus 1 plus cos squared theta, right? And so there's where you're going to get the 2 cos theta. So you get 2 cos squared theta minus 1. Okay, and then from this, we have, that the cosine of 2 theta is equal to 2 cos cos squared theta minus 1. And so it's just a simple matter of doing some algebra here and getting the cos squared theta all alone by itself. And so you'd have 2 cos squared theta equals cos 2 theta plus 1. And then you divide both sides by 2, and you get cos squared theta equals cos 2 theta plus 1 over 2. And technically we had this order slightly different, and so we could say cos squared theta is equal to 1 plus cos 2 theta over 2, right? So that is the form that we started with up above here. Okay, and so as you can see, it's just a simple application of the, it's just basically just an algebraic maneuver on the double angle formula. And the others are going to be the same. They're going to be similar. Okay, they can be derived in kind of a similar way. All right. And so let's do some examples here. We'll do an example with this one. Let's do an example using this. Let's do this example. So let's write an equivalent expression for cosine to the 4th x, right? We want to write an equivalent expression for cosine to the 4th power of x. So cosine of x to the 4th power is the best way to say that. And specifically we want this equivalent expression to not contain higher powers on the trig function. Right? So we want to write an equivalent expression for cos x to the 4th power that does not contain powers of trig functions greater than 1. Right, so we basically need to re-express this thing. So how can we do that? Well, cosine to the 4th power of x. Remember what this is. This is cosine of x all to the 4th power. Right, but even better, we could write it like this. We could write cosine squared x squared. Okay? And so we can use our power reducing formula on everything inside the parentheses here. And so this is equal to 1 plus cosine of 2x over 2, right? That's what the cos squared x is. And so that all is squared like this. Okay. All right. And so then really what we have here is we have 1 plus cos 2x squared all over 4, right? We have to square the top and the bottom. And so let's expand this numerator. And what do we get? We get 1 plus 2 cos of 2x plus cos squared 2x all over 4. Okay. And so we have this. And we can kind of, so we're getting closer, right? We've gone from having the cosine be to the 4th power to instead being squared. But we have this other stuff up front that we have to keep track of as well. So let's go ahead and what we want to do next is kind of break this apart so we can isolate this piece of it. So we're going to have the 1/4, which is this and this, plus 2 over 4 is 1/2, so this will be plus cos 2x over 2. And then you've got this guy over here plus cos squared 2x over 4. Okay, now this numerator section here, I can do the same trick. I can use this power reducing formula on this part here. Okay, and so we could write this as 1/4 plus cos 2x over 2 plus 1/4 times, now what is this? When we power reduce that numerator section, it's going to be this thing here, isn't it? So it'll be 1 plus cos 2x over 2. Okay. And so we've got this. Oh, actually, I gotta be careful here. Be really careful. In the power reducing formula, you go from cos squared x to 1 plus cos 2x. So the angle has to double each time. All right, so down here what I've written is not quite right. We started with an angle of 2x. This now needs to go up to 4x. So let me put a 4x in there instead, okay? So be really careful of that. All right, now we could just simplify this. So let's write 1/4 plus 1/2 cos 2x plus, I guess you've got 1/8, right? So you've got 1/8 plus 1/8 cos of 4x. Okay, and then finally, I guess we could combine the constants here. And so an 1/8 plus a 1/4 is basically an 1/8 plus 2/8. And so I got 3/8 plus 1/2 cos 2x plus 1/8 cos 4x. Okay, and so this guy here, this whole thing, remember, is equal to cosine to the 4th power. Right, and so this is the answer. This is our equivalent expression for the cosine of x to the 4th power that does not contain powers of trig functions greater than 1. Right, it does include some double angles and even quadruple angles, but it doesn't involve powers. Okay, so that's a quick use case for where power reducing formulas can come up. They can come up in other ways as well, but that's just one example. Okay, let's take a look at the last set of trig identities for this section. They're called the half angle formulas. Okay, these are called the half angle formulas. Okay, and again, I'll just write them out. So the first one is the sine of alpha over 2. Alpha is just the Greek letter. Alpha over 2, the sine of alpha over 2 is equal to plus or minus the square root of 1 minus cos alpha over 2. Okay, all right, so this is just chicken scratch there, but so basically what this is saying is that if I have an angle alpha and I divide it by 2 and I take the sine of that half angle, then it's equal to, you can relate it to the full angle using this expression here. Sine of alpha over 2 is equal to plus or minus the square root of 1 minus cos alpha all over 2. Okay, let's write the other ones out. So the cosine of alpha over 2 is equal to plus or minus the square root of 1 plus cos alpha over 2. All right, so real similar there. And then the tangent of alpha over 2 is plus or minus the square root of 1 minus over 1 plus. 1 minus cos alpha over 1 plus cos alpha. Okay, and so that is the trio of the half angle formulas. Now, notice the plus minus. This is something you may or may not have come across. Plus minus means plus or minus. I think we've seen this for sure. Like when you're solving a quadratic equation, you frequently have to take a square root, and when you take the square root, it's possible to have that be plus or minus, and that's what's happening here. Now, in the context of the trigonometry here, though, the plus minus symbol does not mean that we have two possible values like it does in algebra. It means, depending on the context, that one of them will be used or valid, like either the plus or the negative will be useful, not both. Okay. Right. So frequently when we come across this and we're solving equations, the interpretation is that both will work, positive or negative. But in trigonometry, that's rarely the case. Instead, it's one or the other depending on the context. So the plus or minus means either plus or minus depending on the context. Right, so the context will matter here. Okay, and so these are these guys here are derived from the power reducing formulas. So these are derived from the power reducing formulas. Okay, and let's see how that works. Right, so basically in the power reducing formulas we have a theta, and we're going to replace it with an alpha over 2. Okay, so let's see how this works. So in the power reducing formula for sine, for example, we had sine squared theta was equal to 1 minus cosine of 2 theta over 2. Right, and so that's kind of where that starts from. That's the power reducing formula, and we want to start from there. And what we do is we let theta equal alpha over 2. Okay, so then what do we have? This becomes sine squared of alpha over 2 equals 1 minus cos of twice alpha over 2 over 2, which of course is 1 minus cos alpha over 2. Okay, so these half-angle formulas basically capitalize on one of the things that takes place in the power reducing formulas, which is you relate an angle theta to its double angle. Right? But in this case, we don't really want the square, right? We don't want sine squared alpha over 2, but we just want sine of alpha over 2. And so what we do is we then take the square root of both sides. So sine of alpha over 2 is equal to plus or minus the square root of this guy. Okay, and that's where they come from. Right? They all three of them can be derived from the power reducing formulas, from their corresponding power reducing formulas. And it's the same principle in each case. Okay. These are very helpful. Let's see how these are helpful. We'll do a couple examples here. Right? So let's find the exact value. Find the exact value of cosine of 112.5 degrees. That's obviously not an angle that we have on the unit circle, right? So what do we, I mean, this is maybe you guess that this is going to use the half angle formula since you see the half in there. So you'd want to just notice that 112.5 degrees is just 225 degrees divided by 2. Okay, and so cosine of 112.5 degrees is just cosine of 225 degrees over 2, which is equal to plus or minus the square root of 1 plus cos of 225 over 2. Right, and cosine of 225 degrees, we can find that on our unit circle down here. Right, so if we come down here, here's 225 degrees. The cosine is negative square root of 2 over 2. Right, so that means this is equal to plus or minus 1 plus the negative square root of 2 over 2. And that's all over 2. Okay, and we could just do some simplifying here. Right, that can be simplified. And what would we say? We would say that's equal to plus or minus the square root of, and this would, get a common denominator up top. Right, so we would say that's 2 minus the square root of 2 over 2. All over 2. Right, we can do that, and then this would be like 2 minus the square root of 2 over 2 times 1/2. Right, just remember that's over 1. And so what do we get? We get plus or minus, again plus or minus, the square root of 2 minus the square root of 2 over 4. Right, now the question is Is this plus? Is this minus? Which is it? Well, we know that 112.5 degrees is going to have, or sorry, 112.5 degrees is going to have to, the cosine of that angle is going to have to be negative. That'll put us in quadrant 2. And so this would be negative square root of 2 minus square root of 2 over 4. Okay, and so this would be like the best answer. This is the exact value. All right. Okay, very good. Right, so this has practical applications, and you can help you find odd angles, help you find angles that you haven't previously found, based on angles that you have previously found. Okay. All right. It can also be used. These formulas can also be used in trig verification problems. So here's a great example. Well, actually, that's not the example I wanted to do. This one. So let's verify that the tangent of alpha over 2 is equal to cosecant of alpha minus cotangent of alpha. All right. And so in this case, we're going to actually start with the right-hand side because it appears to be the more complex. And so we'll say cosecant of alpha minus cotangent of alpha. This is equal to 1 over sine alpha minus cos alpha over sine alpha. And that means this is 1 minus cos alpha over sine alpha. And this, of course, is equal to the tangent of alpha over 2. Right? We know that this is equal to the tangent of alpha over 2. Now, remember, here all we're doing is we're recalling that tan alpha over 2 is equal to 1 minus cos alpha over sine alpha. Right, this is literally the formula that we started the section with. Okay. And yeah, that's another. So these, all of these have applications for verifying trig identities. Now, there are more complicated identities that will use these in less obvious ways. Like it's kind of obvious when they have a half angle in the identity statement. It's kind of obvious you're going to be using the half angle formulas. But there are examples where these come up in a slightly more subtle way, right? Where the problem doesn't explicitly contain the kernel of its own solution, right? Meaning like you can obviously see how to solve it. So let's take a look at this example, just slightly more involved. Right here we want to verify the tangent of theta is equal to 1 minus cos 2 theta over sine of 2 theta. Right, so again, here we're going to start on this side. So I have 1 minus cos 2 theta over sine of 2 theta. Right, and so then I can write this as 1 minus, now instead of cosine of 2 theta, I'm going to use the double angle formula here. And I know that that's cos squared theta minus sine squared theta. And then down here, I'm going to use the double angle formula for the sine, and that one is 2 sine theta cos theta. Okay. And this is all going to be equal to, so what can we say here? So we know that the cosine, we know we have the Pythagorean identity, right? This is kind of a tricky step here. So we have cos squared theta plus sine squared theta equals 1, right? And that implies that cos squared theta is equal to 1 minus sine squared theta. right? So we have that. And so this guy here is really just equal to 1 minus 2 sine squared theta, isn't it? Right, because I can take the cosine squared theta and I can replace it with 1 minus sine squared theta. And so then I've got 1 minus sine squared theta minus sine squared theta, which is 1 minus 2 sine squared theta. And then down here I've got 2 sine theta cos theta. Okay. Now I still don't have anything close to resembling tangent, so how am I going to get this back to tangent? Well, let's simplify that numerator a little more. Right? And so I've got 1 minus 1. So those basically undo each other, and then I got minus negative 2. So the top is really 2 sine squared theta. It's positive, isn't it? And then 2 sine theta cos theta down below. And so this is looking much better. The 2's cancel. The sine in the bottom will cancel with one of the sines up top. So I have sine squared theta over sine theta cos theta. And again, the sines will cancel, so I have sine theta over cos theta. And so that is just tan theta. Right? That's what we were after. Right? So we verified that this guy here is equal to this guy here. Right, this one was a little tricky. I mean, you can see that you need to use a double angle formula probably to get rid of the double angles, but it's not obvious. Right? It's not it's not a simple swap. Okay, it's a little bit more involved. All right, so I think that will do it. Those are the 3 big identities that we needed to introduce in this section. Next time we'll get into the product to sum formulas and the sum to product formula. So this will take the product of some trig values and change it into a sum or difference, and conversely take the sum or difference and convert it into a product. Right? And so depending on your application, those can be helpful. All right, so we'll leave it there, and we'll talk to you all next time. Take care.